Great. Okay, so yeah, since it's been like 10 days, I thought we would just start with some slow review and then go on to some orthogonal projections more. So this is hopefully a very quick review, just to find the dot product between these vectors. Let's see if you remember how to actually calculate dot products. Product of V equals and W equals 2, 1, negative 3, and 12. Okay, are they orthogonal? So this is a very quick warm up. This is a warm up. And then we'll get on to some orthogonal projections. So whoever, I mean, you can just shout it out or type it in the chat. What do you get? V.W equals something, and yes or no. No, they are not orthogonal, because what do we get? The dot product is what? Negative 8 minus 21, negative 29, 24, negative 5. Great, yeah. Looks like everyone's getting the right answer. The dot product is negative 5, and so they're not orthogonal because in particular, this does not equal 0. And that's what our definition of orthogonal was. Great, okay. Now that everyone's thinking about orthogonality, let's talk about orthogonal projections. So we talked about this a little last lecture. Let's just do it one more time. So orthogonal projections. Let's just go straight into an example that we can do together. Let's find the orthogonal projection of V equals -1, -2 onto W, which is the span of, we'll do a one-dimensional space. So say like this. Okay, so we have a subspace W, which is a one-dimensional subspace inside of R2. You can picture that as a line. And then we have a vector inside of R2, and we're going to project that onto our space. So if we were to draw that, we have R2. Our space is 3, 1. So something like this is a line. This is our W. And our vector is -1, -2. Here's V. And we want to project this onto W. Okay, so, right, this is the drawing we're always going to draw. So the projection is we want the vector that lies on this space that's as close as possible to V. And so you imagine just kind of dropping down a line so that it's perpendicular. And then our projection is this segment of the line. This vector right here is the orthogonal projection. Okay, so it's not the orange thing, right? The orthogonal projection needs to be a projection, so it needs to be on W. And this orange thing is not on W, it's orthogonal to W. Okay, so how do we find this orthogonal projection? We call it proj sub W of V. Right? How do we find it? Well, there's a formula for it, but let's just see if we can figure that formula out. So this projection needs to be on the line W. So it needs to be, in particular, in the span of this vector. So let's just say it's some scalar multiple times this vector, 3, 1. Right? And we want to figure out what C is. Well, the defining property of this is that if you were to subtract the orthogonal projection from V, you should get something orthogonal to W. So if we take V and we subtract it from this orthogonal projection, right, we should get something orthogonal. This is, sorry for all the colors, is orthogonal to W, which means its dot product with anything in W needs to be 0. And just using that, we can figure out what C needs to be. So this implies that, this implies that V minus C times 3, 1, we would take this and we were to dot it with 3, 1, we should get 0. Right, and now we can solve for C. Right, because on one side we have V dot 3, 1 equals C 3, 1 dot 3, 1. So that tells us what C is. C is V dot 3, 1 over 3, 1 dot 3, 1. Right, so this is maybe some review for everyone. Right? So the orthogonal projection, and now this, I mean, you can kind of forget a lot of this derivation almost, because now this is basically the formula we're going to use. So let me erase some of this. Keep that. So, oops. The projection of V onto the space W is V dot 3, 1 over 3, 1 dot 3, 1 times the vector 3, 1. Right, and this is our formula, so we just need to figure that out. Here, V is equal to -1, -2. And so we can just plug that in, and you get some vector. And when you do that, you should get something like, I mean, whatever you get should be like negative, something that, you know, in the fourth or the third quadrant. So that's a good way to check. So, okay, let's just finish that out actually. what exactly is just so we're all on the same page? We get something times 3, 1. So let's just do all these dot products and simplify it. So the first one is -3 minus 2, -5 over 10. Okay, so it does look like it's in the third quadrant. So this is the orthogonal projection. Yeah. So did everyone follow what was happening there? Are there any questions so far? Okay, let's do a harder one. Let's do where W is a two-dimensional space. I'm going to erase all this. Let's let W equal, let's say the YZ plane in R3. All right, so I'm not even giving you coordinates anymore. I'm not giving you the actual vectors that span it, just a visual of what W is. And let's let V just be some vector, like 2, 0, 3. And we want to find the orthogonal projection of W onto V. or V onto W, sorry, which we denote proj sub W of V. Okay, so I can draw you a picture. Well, maybe I can. We got your x-axis. No, oops, that's not what I wanted. You got your y-axis. Here's the axis. And you can imagine the YZ plane. This is the y-axis. Okay, and we have some vector coming out, 2, 0, 3. This is a somewhat of a drawing. Okay. We have our orthogonal projection. And we have the vector orthogonal to it. Okay, more or less a picture. All right, so you don't need to draw this every time you try to figure it out because we have a formula. All right, so we can just plug it into the formula. Right now we just generalize the formula we just had before. So the formula was that the projection I'll do it in green, of W onto V should be V dot some vector B1 over B1 dot B1 plus V dot B2 over B2 dot B2, B2, and where B1 and B2 are yeah, so there's a question here. If you're projecting onto the YZ plane, can you just make the X coordinate 0? Yeah, I mean, that's essentially what you're doing. But we're gonna do it a little more systematically in case W is not the YZ plane, but like some other plane in R3. So we'll do a harder example after this. But you're right, there's just an easy way to figure this out. You should just get 0, 0, 3, because the picture shows it should be, I mean, it should just be like intuitively 0, 0, 3, just make X 0. But if we use the formula, we should get this as well. So B1 and B2 are, you just want to pick any two vectors that span W, but not just any two vectors, actually. They need to be orthogonal vectors that span W. So they need to be what's called an orthogonal basis for W. Right, and this is pretty important, right? You need to just pick any two vectors that span W as long as they're orthogonal. So we could just pick, for example, the y-axis and the z-axis. So 0, 1, 0 and 0, 0, 1. Those would span W, and then we can plug that in for B1 and B2. And we should get 0, 0, 3. So in fact, I'll just do that very quickly, and then we'll do a harder example where W is not so easy. So let's see. I'm gonna erase this picture that I drew so well. So for example, B1 could be 0, 1, 0, and B2 could be 0, 0, 1. Right? It doesn't matter which B1 and B2 you choose as long as they're an orthogonal basis. If I chose a different B1 and B2, then I would still get the same projection. The calculations would be different, but the overall vector would be the same. So we get that the projection is the dot product of 2 with this is just 0 plus dot product of this is 3 over 1 times B2. Okay, great. So we get 0, 0, 3. Exactly what we got. That was an easy calculation. All right, let's do a harder one. Let's do something maybe we can't visualize. So I'm going to clear all this. Let W be the span of some vectors. Let's keep it in R3, that way we can actually visualize it. 1, 0, 1, and negative 1, 1, 1. Okay, and let's find the orthogonal projection of V equals 2, 3, negative 1 onto W. All right, so this is just an exercise for everyone. I'll let everyone work on this for a little bit, and then we'll go over it in a few minutes. I'll try to draw a picture in the meantime. Oh, no. Let's see. 1, 0, 1 looks like this. Maybe negative 1, 1, 1 looks like that. So it's some like tilted plane. Here's W. Kind of tilted a little bit. And then you have vector V. Which kind of just goes like that. So it's underneath the plane. Okay, did someone get an answer? One over square root of 2 W1, maybe. So square root of 2. I think square root of 2 might be, I don't think there should be any square roots. Yeah, so remember this dot product here is, not the, it's just the, the dot product of a vector itself, not the norms, not the square root of the dot product. So probably we have a 1 over 2. Yeah, it seems like people are getting the same thing. Interestingly enough, the dot product with the second vector is 0. Is that right? Negative 2 plus 3. Oh yeah, it is. So it's actually it's already orthogonal to. So that was just coincidence. The V is already orthogonal to B2. This is B2. This is B1. This is V. So in fact, when you calculate the projection, it's just on the first component. So this is our answer. Yeah, so I mean, this formula will work in all these cases. In particular, the cases where it's not just obvious what the orthogonal projection is. or you can't just set one of the coordinates to 0, right? So, oh yes, so one thing we need to make sure, I don't know how many people actually made sure of this, was that B1 and B2 are actually orthogonal, right? Because remember, we need these to be orthogonal. And so it's always good to check that they are orthogonal when we give them to you. And it's pretty easy to check orthogonality, right? So we can just quickly take the dot product of these, and yeah, they're orthogonal, which they are. Great. So, I mean, that's essentially orthogonal projections. And that's essentially what we talked about last Thursday or last Friday. Great question. What if they're not orthogonal? If they're not orthogonal, then let's see. We're going to learn about this. I don't know when, so I don't know when I should go over it, but let's see. Let's say you're given a space W. It's a span of some vectors, W1 through Wn. And you want to find the orthogonal projection of some vector V onto W. But let's say W1 through Wn are not orthogonal. They could be linearly independent, but they may not be orthogonal. So the question is, what do you do? What to do? So we are going to learn about what to do. And I can go over it now, but it might be going ahead of lecture. So before, maybe I should pause and see if there are any questions at the moment. If not, then yeah, let's talk about what to do here. So what we're going to do is we make them orthogonal essentially. We find an alternate, or let's see, yeah. We're going to construct an alternate basis for W that is orthogonal. We construct an alternate basis, an alternate spanning set, I guess. W that is orthogonal. And we do this from the original vectors, from W1 through Wn. All right, so we're going to take them and we're going to construct another spanning set, and we're going to make it orthogonal. And this process, it has a name. This process is called, I'll switch to black now. It's called Gram-Schmidt orthogonalization, the Gram-Schmidt process. Right, named after mathematicians Gram and Schmidt. Or at least I think they're two different mathematicians. And what it does is you start with, what this does is you start with some vectors like W1 through Wn, and you perform this process called Gram-Schmidt, and this converts them into another collection of vectors that are orthogonal, and they span the same space. So how does this work? Let's do a small example. Yeah, great question. If a spanning set has only one vector, is it automatically an orthogonal set? Yeah, because an orthogonal set is a set of vectors where each one is orthogonal to every other one, but there's only one, so there's nothing to check. It's like how a spanning set with only one vector is also automatically linearly independent. I mean, as long as it's not 0. So if S equals a single vector, then S is orthogonal. And also linearly independent. Right, as long as V is not 0. Okay, so let's do a small example. Let's say S is 2 vectors in R2 that are not orthogonal. So let's do 1, 0 and 1, 1. So these are 2 vectors that are not orthogonal, right? We have 1, 0 and 1, 1. No, that's 1, 1. 1, 0. And this is in R2, so they're not orthogonal. Okay, let's call this something. Let's call this W1 and W2. And so what we want to do is we want to make them, really this problem is this W2. It's kind of not orthogonal to W1. And we kind of want to subtract, what our goal is, we're going to subtract off the parts of W2 that are not orthogonal to W1. So we're going to construct V1 and V2 with V1 dot V2 equals 0 and the span of V1 and V2 equal to the span of W1 and W2. So I think the book might use different notation. So sorry if this confuses for now. And so step 1, we're just going to let V1 equal W1. Right, that's the easiest way, because just like we noticed that a single set with one vector is automatically orthogonal. So we can just let V1 equal W1. The process that we're going to do is kind of be iterative. So we're going to start with a set, say with 2 elements, and we're going to pretend it has 1 element and do this process, then add another element and keep going. So for step 1, V1 equals W1, and then step 2, right? If we want the spans to be the same, we would like V2 to be W2. But there's a problem, which is that these 2 are not orthogonal. And so we can't do this. But what we can do is we can subtract off some parts of W1, let's say CW1, and we want to figure out what C is. So that V1 and V2 are orthogonal. So you'll notice that by subtracting off a scalar multiple of W1, the span of V1 and V2 is the same as the span of W1 and W2. Right? So doing this subtraction doesn't change the span of W1, of V1. Yeah. So by which I mean the span of V1 and V2 equals the span of W1, W2. And so now we just need to figure out what C is, and that's the same process we did with orthogonal projections. All right, so now we want V1 and V2 to be 0, so we just take the dot product with everything, and we figure out what C is. All right, so we get that we want V2 dot U. Okay, so let's just take this dot product. So we get W1 dot W2 minus CW1 equals 0. We solve for C. We get that C is W1 dot W2 over W1 dot W1. All right, and then that's our formula for C. And so let's just do this with this example and see what we get. So let's erase some of this. So V1 is W1. V2 is W2 minus something times W1 minus, and then this C is going to be what we found here. So it's 10.11 over 10.10. And so we just figure this out. It's 1 minus 10, we get 0, 1. Right, so we get the standard basis vectors, 1, 0, and 0, 1, and these are orthogonal. So what exactly, so this is Gram-Schmidt. We took a linearly independent vectors, W1 and W2, that were not orthogonal, and we constructed another basis of our space R2 with vectors that are orthogonal. And what exactly did we do here? Here's W1, let's say. I'm going to blow this up. W1, W2. This is the XY plane, R2 plane. Or I guess it should be like this. Okay, and all we did was we looked at this and said W2 is not orthogonal to W1, but let's just subtract off the part that makes it not orthogonal. Right, we subtracted off this part. Right, all we kept was this part. This is the orthogonal projection, W2 on the W1. Right, you'll notice that this, oh, sorry. This is the orthogonal projection of W1 onto W2, W2 onto W1. And so if we subtract that off, so this green part, this is the orthogonal projection. If we subtract that off, we get the green part, which is what we're doing. So the whole thing is this green part. And that's what Gram-Schmidt is. So it's a little confusing at first, but let's do a bigger example. I'm going to erase all this. Let's say W is the span of W1, W2, W3. All right, we have 3 vectors, and they're not orthogonal. We're going to do Gram-Schmidt on them. Let's perform Gram-Schmidt. Let's keep it like a little more general, and then we'll put them to numbers. So step 1, we're going to do V1 is equal to W1 to obtain orthogonal V1, V2, V3. All right, so V1 is going to be W1. V2, we'd like it to be W2, but it's not orthogonal to W1. And so we can subtract off, if we subtract off its orthogonal projection onto W1, then by definition, this is orthogonal, right? So this is now orthogonal to W1, right? Because here's W1. So it's the same picture. Here's W1, here's W2. The orthogonal projection is, oh shoot. The orthogonal projection is this bit. Subtracting that off gives us this bit, which is orthogonal to W1. And we'll notice it's the same, the span of these two vectors, the black one is two black vectors is the same as the span of W1 and this green vector. But now they're orthogonal. All right, and now we're on to V3. V3. We like that to be W3, right? But W3 is not necessarily orthogonal to W1 and W2. So we should subtract off its projection onto these first two vectors, onto space spanned by W1 and W2. Right, we take W3, subtract off its projection onto the span of these two, and we now get a third orthogonal projection. Right, so the picture now is now three-dimensional. So we have a space. Here's maybe W1 and W2. And we have some other vector, W3. And it's not necessarily orthogonal, but if we subtract off the projection onto this span of the first two vectors, we do get something orthogonal. So this is now orthogonal to span W1 and W2 because it's this vector. It's the vector projection. And this is Gram-Schmidt. And you just keep doing this over and over again. So let's do maybe a concrete example. And then we'll get the hang of it. So let me find one. Well, let's just see if we can make one up. Okay. Let's let W equal the span of 2, 1, 0. I don't know, -1, 1, 1, and 0, 2, 3. Okay. I don't know how the calculations might be a little messy, but let's just figure this out. W1, W2, W3, and let's perform Gram-Schmidt. To obtain an orthogonal orthogonal basis for W. Basis V1, V2, and V3 for W. Okay, so V1, let's just make that equal to W1. You'll notice that the order we choose W1, W2 in and W3 in does actually affect the outcome. Because there are many different orthogonal bases for a space. So just picking one gives you just one orthogonal basis. Now V2, we want it to be W2, but we want to subtract off the orthogonal projection of W2 onto W1. Okay, because now this is what's going to be orthogonal to W1. So it's W2 minus, now the orthogonal projection, we know how to do this. This is, here's W2. Sorry. right? It's the dot product of W1 and W2 over the dot product of W1, W1, W1. So I'll just write that out slowly. Which is something. So maybe we can actually figure this out. -1 over 5, 2, 1, 0. Okay, so it's not that's not the nicest calculation. -1 plus 2/5. Okay, and now V3 is W3 minus the projection of W3 onto the span of W1 and W2. All right, this one we're gonna need some more space. So I'll just write what we found for here. Erase this. Okay, so now we need to subtract off the projection of W3 onto these. So all this just like subtracting off orthogonal projections. And it's pretty easy to mess up all your vectors. So you just want to take it a little slow. Okay, so we want to subtract off the projection. So let's just calculate this first bit here. All right, so we have the span of two vectors, right? And the orthogonal projection. Let's do this. Let's do this one separately. Yeah. Right, so the projection of W3 onto the span of two vectors, right, is W3 dot something over something dot something plus right, this is the formula where we need to plug in some of these vectors, right? So we don't want to plug in W1 and W2 though, because remember the orthogonal projection needs to be projected onto an orthogonal basis. So W1 and W2 are not orthogonal, so we need to plug in V1 and V2. So here, V1 is 2, 1, 0. And then we plug in V2 here. Okay, whatever that is, V2, V2, V2. I'm running out of room here. And you plug that in, you get something, and that's what you get right here. And then you get some other vector. And then the collection of those three vectors are your orthogonal basis. So we're gonna do a lot more examples of this, but basically the long-winded answer is that if you need to find orthogonal projections and you're given a space of vectors that is not orthogonal, then you need to perform Gram-Schmidt, which is this process that kind of finds a basis that is orthogonal. And it does it just by iteratively subtracting off orthogonal projections. So one last picture, maybe here's W1, maybe here's W2, maybe here's W3. Maybe this is in R3, for example. You want to find a basis that is orthogonal, and these are not orthogonal. And so what you can do is you can subtract off the orthogonal projection of W1 to W2. So you get this vector, and then you subtract off projection of W3 under the space spanned by W1 and W2. And so you get these three vectors as your orthogonal basis, right? Although they're vectors, so they're like this and like this. And now these three span the same space, but they are now orthogonal with everything. This is a picture of Gram-Schmidt. Picture of Gram-Schmidt. Okay, so why don't I'll just stop there for a brief second. We can take questions. We can go back to, this is getting ahead of the lecture. I don't think you've talked about this in lecture yet. So I think you'll talk about it probably on Tuesday, tomorrow, or on Thursday. So, we're definitely gonna go over this more.
I have a question.
Mm-hmm.
So if you take the cross product of W1 and W2 in this example, mm-hmm. would that give you an orthogonal vector that's
yeah, good question. So we know some things about cross products. That cross products of two vectors in R3 give you a third vector that's orthogonal to those two. In this case, yes, just because we have three vectors in R3, so their span is all of R3 if they're linearly independent. And so if you just take the first two and take the cross product, that should give you kind of, plus or minus that will give you an orthogonal basis for W. But I should say that that's really only special to R3. Yeah, so the question was like, instead of doing Gram-Schmidt, couldn't we just take cross products? Or would that be the same? And the answer is yes, it would in this particular example, but not in every example, because the cross product only makes sense in R3, right? You can't take the cross product of vectors in R4, for example. There's no such thing. Or in R2, or in anything but 3, essentially. So this is more general than cross product.
Okay, thank you.
Mm-hmm. I think, have we talked about orthogonal complements? We can talk about it. We did a little when we're taking orthogonal projections. We want the vector minus its orthogonal projection to be in the orthogonal complement. We can do another example. Let's do another example actually, where we talk about orthogonal complements. I kind of forgot about that. Let's move this out of the way. Okay. Let's do another problem. Let's calculate. The orthogonal complement of the space. Let's do which would be an R4. Let's just make it easier. 0. What I mean by calculate is I mean describe describe the space. Usually we describe spaces as we give them spanning sets. So it's 11 right now, but I think there's some advice that I could record my first section from 10 to 11 and then keep 11 to 12 open for free discussion and other examples. So I'm going to kind of keep going and maybe just keep this open for any other questions people have. But let's do this particular one where we want to describe the orthogonal complement of the space. So how do we do that? Let's remember what this means. The orthogonal complement of a space W it's all the vectors that are orthogonal to every vector in W. So it's denoted W perp. This is called W perp. And it's the set of vectors. So this is in whatever space you're in, such that this V has to be orthogonal to everything in W for all W in W. So this is the definition of orthogonal complement. And W is an infinite, it means a space infinitely many vectors. So it seems like you have to check infinitely many vectors in this to see if it's actually in the orthogonal complement. But remember, any space here is described by a basis, which is finitely many vectors. So you really need to just check dot products in finitely many vectors. So, fact. If B1 through Bn is a basis for W, or even just a spanning set for W, then V is in W perp if and only if you just need to check its dot product on these finitely many vectors. V dot B1 equals V dot B2 equals dot 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 V dot Bn, they all equal 0. All right, and this is how we're going to find orthogonal complements, because I can just rewrite this. Each one of these is, remember the dot product is another way to say this is V transpose B1. So it's the matrix product where V transpose is now a row, B1 is a column. So this is a 1-by-1 matrix, which we identify with a real number. Right. And we can just write this all in a matrix form. So we get V transpose times the matrix, whose columns are B1 through Bn, this equals 0. Which is kind of backwards what we want, I realize. So there's another way to write this. Instead of V transpose B1, it's also B1 transpose V and B2 transpose V. So this is if and only if, I'll write it here. Oh, no, let me start over. So V is in W perp, if and only if. So I can just take the transpose of all of this. or just rewrite this all as B1 transpose V and so forth. And I get, if and only if you take the matrix whose rows are B1 through Bn, and you multiply it by V. There's only a single V. Equals 0. And this is how you describe orthogonal complements, right? So V is in W perp if and only if, or V is in, so it needs to satisfy this matrix equation, which is saying that it's in the null space of this matrix, is in the null space of the matrix you get by just taking any basis of W and forming a matrix with the rows being those basis vectors. So B1, Bn, this is a matrix. Where B1 through Bn is just a basis for W. Where B1 through Bn is basis for. So is there a question? Don't you just have to test V with one basis vector? No, it needs to be orthogonal with all the basis vectors, not just one basis vector. Right, to be in W perp, it needs to be orthogonal not just to any old vector in W, but to all vectors in W. Right, so you have to test it against all of the vectors. So for example, like, you know, if W was 1, 0, 0, you know, the span of this. Right, but that's just because the basis vectors themselves are orthogonal doesn't mean that you just need to test it against one basis vector. So, I mean, so for an example, let's do the span of 1, 0, 0 and 0, 1, 0, right? And we want to say V is in W perp. We want to find, let's say, V in W perp. We could test it against this first basis vector. We could say something like, if we set V equal to 0, I don't know, 2, 0, then V dot the first basis vector is 0, but V is not in W perp. V is not in W perp because it's not orthogonal to the second one. So it needs to be orthogonal to every basis vector in W, or to every, you just pick a basis and it needs to be orthogonal to every one of those basis vectors. So that's why we need this whole matrix equation. So let's just finish this example. To find the orthogonal complement, we're going to find basically the null space of the matrix we get whose rows are these two. So a spanning set for W perp is a spanning set for the null space of the matrix 1, 0, 1, 0, 0, 1, 0, 1. But I mean, now this is great because I mean we just formulated what it is to describe an orthogonal complement as what it is to describe a null space, and we know how to describe null spaces. We can put this matrix in row reduced echelon form. In fact, it's already in row reduced echelon form, and then we can solve for our pivot variables in terms of our free variables and so forth. So we get x1 plus x3 equals 0, x2 plus x4 equals 0. And then we get maybe x3 and x4 are free. So x4, we need some more room. There's a question, does a spanning set have to be linearly independent or just spanning? A spanning set, by definition, just has to be spanning. So when we say describe in our describe a space, a spanning set is usually good enough to describe the space, but I mean, it's always nice to get a basis. So in fact, we're gonna find a basis for the null space, so we might as well just replace these all with bases. I mean, it's true that if I rewrite this, a basis is a basis. Yeah, might as well make them linearly independent. But it's also true if I wrote spanning set. Okay, so we get that. I'm gonna put it up here. So this is our, in parametric form, these are our solutions to the linear system. And so we get that a basis is -1, 0, 1, 0, and 0, -1, 0, 1 is a basis for the null space of this matrix, and in particular for W perp. Yeah, and a good thing to check, I mean, now that we have a basis, it's very easy to check that like this makes sense. So we can just go through, because dot products are very easy to calculate. We can go through one by one, we take this first basis vector and just make sure it actually is orthogonal to these two, right? We just do that pretty quickly, right? Let's just take the dot product of this first one with 1, 0, 1, 0. Yeah, that's 0. Same with the second one. And so, you know, it's very easy to check that these two are in fact orthogonal to our original two vectors. And so they are actually in the orthogonal complement. So any questions on what we did here? Okay. Well, in that case, I'll maybe recap a little and then just leave this channel open for any other questions. I do have office hours today at 3:30, the same link, same Zoom ID. So maybe a recap. We have this formula for orthogonal projections. V dot B1 over B1 dot B1, B1 plus V dot Bn over Bn dot Bn, and where B1 through Bn are orthogonal basis for W to describe orthogonal complements. We describe null spaces. We describe null space of the matrix whose rows are a basis of W. B1 through Bn are basis of W. And then lastly, you know, right here, we went ahead of the class a little. If this is not orthogonal, if B1 through Bn not orthogonal, we perform Gram-Schmidt to make them orthogonal. Yeah. Or not really to make them orthogonal, but to find another orthogonal basis. To find another orthogonal basis. Okay, so those are kind of the three things we talked about today, and we'll go over this more as well on Wednesday. So I will end there. I'm going to stop recording.